Hello and welcome to chapter 4, if I can find it on my desktop here. Goodness gracious, I'm so sorry. Um, okay, so chapter 4, we're going to start talking about the solar system. So far, you've learned a little bit about astronomy, a little bit of astronomy orientation. You've learned history of astronomy. You've learned about light and you've learned about telescopes. So, light is basically how we gather any information, and telescopes is the instruments that we use in order to gather that information. And you learned some things about Newton and the atom and how photons can make electrons move to higher states, so they absorb photons, or they can go back to ground state and they release a photon. And then with our telescopes, we gather that light and then we can analyze it and figure out the composition. We could figure out other things, which we're going to still talk about all those. But now we're actually going to start talking about objects in space. We're going to start with the solar system, and then we're going to move out to stars, and then we're going to talk about some weird stuff. So the solar system is where we're going to start, and here we are. This is a comet it's basically a big chunk of ice that orbits between Earth and Jupiter. I think this is an actual picture. Sorry, my dog is an idiot, if you can hear that. So in chapter 4, we're going to talk about an inventory of the solar system. So what objects do we have in the solar system? We're going to talk about interplanetary matter, our major theory about the formation of the solar system, and then planets that we've discovered outside of the solar system. Okay, here are our learning objectives. And when you read the book, you should skim those a little bit. Also, I just wanted to say that since we're probably going to run out a little bit of time, if you can think of something that interests you, you can go actually read ahead in like chapters 14, 15, 16, 17, those kind of things. We're going to cover them really fast, probably in the last week. So if there's something that interests you, I invite you to go find that book or that chapter in the book. I actually used to read in my astronomy class in college. I actually used to read ahead. It was like the only class that I read the book religiously. Anyway, all right. Side note there, sorry. Okay, so an inventory of the solar system is where we're going to start. So here we have our vocabulary. We're going to describe the scale and structure of the solar system and list the differences between the terrestrial and Jovian planets. So early astronomers knew about some of our items. So they knew about the moon, stars, Mercury, Venus, Mars, Jupiter, Saturn, comets, and meteors. Those are the things you can see with the naked eye without too much trouble. Now we know that the solar system has one star, at least 173 moons orbiting 8 planets. We added Uranus and Neptune. Of course, we added Pluto for a while and then it got demoted. We've got 7 asteroids that are rather large, I should say. We've got millions of asteroids, comets, meteoroids, 5 dwarf planets that we've discovered so far, and over 100 Kuiper Belt objects. And above the numbers there are kind of above a certain size. I work for Rubin Observatory, and we took data last summer for just a couple of nights or whatever, and we're able to discover like 2,000 asteroids in just a couple of hours of observing. It was crazy. If you go into the Rubin Observatory website, rubinobservatory.org, there's some videos and stuff you can look up for that. Okay, so here we kind of have a picture of the inner solar system with the sun at the center, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, and then the Kuiper Belt. We also have the asteroid belt in there between Mars and Jupiter. My very energetic mother just served us nothing. When I was a kid, it was my very energetic mother just served us 9 pizzas, but since Pluto got demoted, now it's just nothing. Okay. There we go. All right, so here it's kind of hard to see, but you get this graphic is in the book if you're interested. Properties of some solar system objects. So we've got the planets here: Mercury, Venus, Earth, the moon, Mars, Ceres, which is an asteroid in the asteroid belt, Jupiter, Saturn, Uranus, Neptune, Pluto, which is a Kuiper Belt object, comet Hale-Bopp, and then of course the sun. And so here we've got their semi-major axis, or the distance between the sun and the object, with the Earth being at 1. Orbital period in Earth years, Earth being 1. Masses, if we compare everything to Earth's mass, Earth is 1. We're just doing a comparison here. That's pretty much how it's easier to do like comparisons like that with astronomical stuff. The radius of the Earth, if we say the Earth's radius is 1, we got this. Number of known moons we've got here. And then, of course, our average densities. And Earth is at 5,500 kilometers per meter, kilograms, I'm sorry, per meter cubed. And it is the most dense item in the solar system. Look at that. Mercury is close. Venus is next. The moon and Mars are kind of fluffy. Ceres is also fluffy. Jupiter. Saturn here is right here. That's an interesting one. We're going to get to that in a second. Okay, so let's look at these. So the semi-major axis, Mercury is at 0.39 astronomical units. Venus is at 0.72 astronomical units. Mars is at 1.5. Jupiter is at 5.2. Saturn's at 9.8, etc. So we go like this is close to 20, that's close to 30, that's close to 40, which I think is kind of interesting. Orbital period also increases as we go out, so it takes longer to go around the sun. Jupiter, it takes almost 12 years to go around the sun. Saturn, it takes almost 30 years to go around the sun, where Mars is like 2-ish years. All right, masses. Mercury is smaller. Venus is very close, but smaller. The moon is a lot smaller. Mars is smaller. Ceres, very small. Jupiter, huge, humongous. But look at the sun. Compared to the Earth is 1. The sun is 332,000 times bigger. Radius, also small, comparable, small, 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 big. So the radius, there's 11, so it's 22 across Jupiter to get 22 Earths across. Number of known moons, we have 1. Mars has 2. Jupiter 67, Saturn 62, etc. These numbers have changed since this book has been published, and it's a lot bigger now. So here we talked about density before, but if we look at Earth being 1, Saturn is not very dense at all. In fact, Saturn, if it was in a bathtub, would float. So I think we have a picture of that later. All right. So an inventory of the solar system we're still talking about. So distance from the sun is known by Kepler's laws, which the p squared equals a cubed thing. The orbital period can be observed. So Tycho Brahe did lots of that observational data and wrote it down. Radius is known from the angular size. So if we can know the distance and we know the angular size, we can sort of know the radius of the planet. Masses are known from Newton's laws. The rotation period is also known from observations, although some of the planets proved to be challenging to figure out what their rotation periods were. And the density can be calculated if we know the radius and the mass. So pretty cool. There's some, I think one of the things about astronomy that's interesting is that we can know so many things just from understanding math and stuff. So all right, let's go. So here we have a nice orientation. Most of the planets, all of the planets kind of orbit in the same sort of plane. So if you think like a record player, all the planets are really close on the outs. You know, the sun is at the center and all the planets are basically rotating around at the same plane. And so every once in a while, we get these really cool planetary alignments. The news will make it sound like it's amazing, but sometimes it's like spread across the sky and they're including Neptune and Uranus, and you can't see Neptune and Uranus with the naked eye. So anyway, I think I've only seen Uranus once through a telescope, and it was very hard to spot because it's very teeny tiny, so far away. Anyway, also Mercury is sort of a bucket list item. I'm not sure that I've ever seen Mercury, although I might have one time when I was in Arizona, but I've Can't remember now. Anyway, so here we have Mercury, Venus, Mars, Saturn, and Jupiter all in one picture, which is actually kind of cool. When it happens, it's nice to look at, but the news always makes such a big deal and people ask me about it. And I'm like, it's not going to be that spectacular. A couple years ago, though, we did have Saturn and Jupiter next to the moon. And so it looked like a smiley face, which was actually quite cool. All right. So here is a representation of the angular distance that we have that we kind of talked about before. One of my other students called this the big floating eyeball in space. So if we have a known distance to an object, as I said before, and we could sort of see the angular diameter, so we can sort of figure out how many arc seconds it looks like. If we know the distance to the object, then we can actually measure the diameter of the planet. So that's with Kepler's law, we figured out the distances with our understanding of angular measurements. We can look at it and measure how big it is. And then we can, since we know the distance, we can figure out what this, because it's just a triangle and we know how to use trigonometry to work on triangles or geometry. Which one is it? I guess it's geometry. I don't know. It's one of those two. Anyway, okay. So as I said before, all orbits but Mercury are really close to the same plane. Mercury is kind of, remember we talked about eclipses just a little bit in chapter, I just recorded the video yesterday and I can't remember which chapter it's in. Anyway, remember I said that the moon is tilted about 5 degrees from the plane of rotation, and it's kind of the same thing. All other planets are very, very close to the ecliptic, which is on the same plane. Mercury is a little bit off. Pluto is even more off, but it's no longer on this chart because it's not a planet. All right, so here we have sort of a cute little representation about the size of all of these. The sun is huge compared to everything else in the solar system. And so here we have Mercury, Venus, Earth, and the moon, Mars, Jupiter, Saturn, Uranus, and Neptune. Uranus is funny like this because it's actually tilted on its side, which is very strange. Also, the moon is, we almost have a double planet situation. The moon is quite large compared to other moons on other planets like Mars. The two moons they're basically just captured asteroids. They're really, really tiny. But our moon is quite big compared to the Earth. It's kind of the same thing with Pluto and Miranda, but anyway, we'll talk about that more. The 4 moons of Jupiter, I think, could all be bigger than the moon. And the moon, I think, is slightly bigger than Mercury, or Mercury might be slightly bigger. Anyway, we'll get to that. All right. So cool. I get so nerdy about this. All right. So the terrestrial planets, we have Mercury, Venus, Earth, and Mars, my very energetic mother. And the Jovian planets, or the gas giants, are Jupiter, Saturn, Uranus, and Neptune. And you have to be careful when you're saying Uranus, right? I have a daughter named Miranda, which is a moon around Uranus. And I have a daughter named Sharon, or Karen. It's spelled with a CH. And that's the moon around Pluto. Oh, that's what I meant Pluto. I meant Karen when I said, did I say Miranda? I meant Karen when I talked about Pluto a second ago. Forgive me. Got my children mixed up. Oh no, don't tell them. Okay. So here's a comparison between the 2 different types of planets. Now, when we have done studies out in other exoplanets, which are planets out around other stars, there are some unique types of planets that we do not have represented in our solar system. But here are the 2 types of planets that we have on our solar system. So terrestrial planets and Jovian planets. Terrestrial ones are close to the sun. The Jovian ones, the gas giants, are far from the sun. We have closely spaced orbits here, where they're widely spaced here. Smaller masses, larger masses, small radii, large radii, mostly rocky. Ours is very wet as well. Predominantly gaseous. I can't see that because the zoom controls are in the way. Today, they're really, really high. Okay, there we go. Solid surface, no solid surface, high density, low density, slower rotation, very fast rotation. The gas giants rotate very fast. The rocky planets have weak magnetic fields, but the gas giants have strong ones. We have no rings on the inner solar system, but they have many rings in the outer ones. In fact, all four of these have rings, even Jupiter. And we have very few moons over here, but they have lots and lots of moons. Okay. So the difference between the terrestrial planets, though, the atmospheres and surface conditions are very dissimilar through all of the four rocky planets. Only Earth has oxygen in the atmosphere and liquid water on the surface. Earth and Mars rotate at about the same rate. Mars has a 24-ish hour day. It's a little bit longer, I think. Venus and Mercury, their days are much longer, so they rotate much slower. Venus rotates also in the opposite direction, which is kind of crazy. Earth and Mars have moons, but Mercury and Venus don't. Earth and Mercury have magnetic fields, but Venus and Mars don't. So, all planets orbit counterclockwise as viewed from above Earth's North Pole. So this is that 3D thinking. If you think of the sun in the center and you're looking down on the sun, they go counterclockwise. So if you think of the sun in front of you and 12 is the top, they go to 11 kind of thing. All of them have roughly circular orbits, as we talked about before, and they're pretty close to the ecliptic plane. Terrestrial planets are rocky and Jovian planets are gaseous. So there we go. Okay, interplanetary matter. So there is a bunch of stuff out there as well, and there's a bunch of vocabulary here. So we're going to talk about the orbital and physical properties of asteroids. Asteroids and meteoroids are fragments of rocky material. So sorry. Asteroids are basically, they're just larger than 100 meters in diameter, which is just a arbitrary cutoff that we scientists have made. A meteoroid, though, is smaller than 100 meters in diameter. Comets are predominantly, icy rather than rocky, and they're typically 1 to 10 kilometers in diameter, so they're pretty big. Kuiper belt objects, it's the Kuiper belt is the outer asteroid field, basically, and it includes Pluto. And then a dwarf planet, the definition of a dwarf planet is a body that orbits the sun, is massive enough for gravity to pull it into a spherical shape, but not so massive that it cleared the region around its orbit of smaller bodies. So since Pluto is in the Kuiper belt and there's lots of other objects in the Kuiper belt, it got demoted, basically. And I think actually one of the other objects past it is actually bigger than Pluto, I think. Anyway, all right. So here at the inner solar system, we've got this is a graphic that shows the asteroid field and then the Earth crossing asteroids and Trojan asteroids. So we have the sun, we've got Earth here, we've got Earth crossing asteroid in this red, we've got the asteroid belt, Mars, the asteroid belt, and then we get Jupiter. And because of Jupiter's gravity with the sun, there's this sweet spot here before it and a sweet spot here behind it where like asteroids are just sort of hanging out. They don't, they just get to hang out there and there's in balance with the sun and Jupiter. It's kind of weird. Rubin Observatory, one of the missions is to find and catalog Earth crossing asteroids. So NASA put out a call. And so one of the reasons why we got funding to build the telescope was because we have a mission that will identify hazardous asteroids. So here is a path of Icarus and Earth crossing asteroids. So this was a longer exposure. It's in visual if you're looking at the graphics in the book. This is radio, infrared, visual, ultraviolet, X-ray, and gamma rays. And so this is a visual image. So sometimes when we see pictures with composite stuff in there, they'll have two of these letters highlighted. Anyway, so this is a longer exposure. And during the exposure, the light from this asteroid made a streak, which is kind of cool. That's how we found all these other asteroids at Rubin. So asteroids and meteoroids have a rocky composition, but asteroids are bigger. So here we have some different pictures of asteroids. Pretty cool. They're just kind of clumpy and weird looking. Okay, so the dinosaurs may have been killed by an impact from a large meteor, or a small asteroid. So the larger the impact it is, the less often we can expect it to occur. Okay, so this is sort of like hazard analysis kind of 101. In another job, I was a safety analyst. Um, so if something is very, very, very bad, thankfully, it doesn't typically happen very often. If something is not very dangerous, it can happen all the time, right? So here we have megatons of TNT equivalent energy, and over here we have approximate frequency of impacts. So monthly, we have very teeny tiny little things. Every year, we have an annual event with 5 kilotons or so. Every decade, every century, every millennia, this is the Tunguska event, which was an airburster event that happened over Russia, downed a bunch of trees. You should also look up the Chelyabinsk event, if you could spell that. I might have some charts on it later. I'm not sure. Anyway, and then of course, here we go with the more and more energy. We've got a global catastrophe threshold. This is where we have the extinction of the dinosaurs. So this happens every million years or so. And of course, this was 65 million years ago, according to their records. So I don't know. Anyway, so there we go. Here's asteroid Eros. Yeah. This is 10 kilometers apart, 2 kilometers apart. There's a boulder kind of sitting up there, and these are impact craters. So other things have hit it and made dents in there. All right. Most asteroids orbit in the asteroid belt between Mars and Jupiter, but there are Trojan asteroids that are within Jupiter's orbit about 60 degrees ahead or behind. They're at this special orbital place called the Lagrange point. Earth-crossing asteroids have orbits that intersect Earth's orbit and could eventually collide with us. If you've seen that Bruce Willis movie, I can't remember the name of it now. Anyway, disaster movie. They had to go up and like blow up the asteroid with. Anyway, okay, so learning objective 3, describe the composition and structure of a typical comet and explain what a comet's orbit tells us about the probable origin. I'm going to date myself now, but I was able to see Halley's Comet when I was in college. Okay, comets are icy with some rocky parts. The basic components of a comet are the tail, nucleus, hydrogen envelope, ion tail, and dust tail. So here we have sort of a picture of one, a drawing of one, and we actually have a photograph of a comet, and then we also have a photograph of the nucleus here. So the sun is here, the comet is going around, the solar wind kind of melts the comet because it's mostly ice, and then the dust and gas that are sort of melted off trail behind it and make a trail behind it and make a tail. So we have this coma, the nucleus in here, and the tail. Here is Halley's Comet, which, as I said, I'm dating myself with that. It's kind of cool. It comes by every 77 years or something, and 2 of our our meteor showers throughout the year are from Halley's Comet debris, which is kind of cool. Here is a picture. I don't remember which one this is, but here is a picture of a comet. I believe this was taken somewhere in the desert, Arizona potentially, or California maybe. So here is the dust tail that comes off, and here's the ion tail. So the ions and the dust are affected by the solar wind, but they're affected a little bit differently because the ions are stripped of their electrons, and it acts slightly different than the dust tail. So the solar wind means that the ion trail always points away from the sun. The dust tail also tends to point away from the sun, but the dust particles are more massive and lag somewhat, which makes them curve. The solar wind has a stronger influence on the ion tail. So it's coming in and it's starting to melt. The tail is pointed away from the sun, and as it goes around the sun, the tail is still pointed away, and now it's still pointed away, right? So it was traveling in front of the tail, and now the tail is in front of the nucleus here. All right, jets carry gas and dust away from the comet as the nucleus is warmed by the sun. I don't have any charts in here about 3i Atlas. There was this if you have any questions, email them to me, and we might even have a discussion question on that. But um, the one Harvard professor like threw a bunch of junk out and like did this thought experiment on whether it was a spaceship 3I Atlas that came through this year. And it was like, okay, well, I appreciate your thought experiment that you're doing, but all the news outlets picked it up like you were actually saying it was a spaceship kind of thing. So anyway, all right. So we're still talking about interplanetary matter. Now we're moving past we're the Kuiper Belt, and we're talking about comets now, which come from the Kuiper Belt or the Oort cloud. So the size, shape, and orientation of cometary orbits depend on their location-ish. So a comet will come in and we'll be able to like track back where it came from. We're able to do the math on the orbital mechanics of that and figure out where it came from. And it appears like there is a place where all these long period comets come from. So it's called the Oort cloud. Comets rarely enter the inner solar system. So Oort cloud comets rarely enter the solar system. Their orbits can be highly elliptical, but shorter period comets kind of come from the Kuiper Belt. So we have the inner solar system, we have the asteroid belt, we have the outer solar system, we have the Kuiper Belt, and then we have the Oort cloud. Now, Kuiper Belt objects have been found. Oort cloud is technically still theoretical. Nobody has actually photographed anything that they've recognized was in the Oort cloud. So I like to sort of like stress that. So here's like the inner solar system. And if we zoom in on that, we've got all of the planets and everything, but then here's the Kuiper Belt, which looks like the asteroid belt-ish. But then the Oort cloud is this theoretical cloud where all this debris is sort of out there at 50,000 astronomical units away. So 50,000 times farther away from the sun than the Earth. Okay, where the Kuiper Belt is only 50 times as far. I think that's all we need to talk about there. Okay. Summarize the orbital and physical parameters of meteoroids and explain how these bodies are related to asteroids. All right, so meteor showers are associated with comets. They are debris left over when the comet breaks up. So here is, all right, so here's the sun and the Earth, and a meteor shower occurs. So the comet is went through here and it left some debris in its path. And when the Earth intersects that, we get meteor showers because we have junk that we're flying through that burns up in our atmosphere. And so, cool, huh? All right, shooting stars are meteors. They are a sudden streak of light in the night sky caused by friction between the air molecules in Earth's atmosphere and the incoming piece of the asteroid, meteoroid, or comet. A meteoroid is described as a chunk of debris or small interplanetary fragment. It's the most common source of meteors. A meteorite is any piece of interplanetary debris that survives the fiery passage through the atmosphere and it finds its way to the ground. So you see it up in the sky, it's a meteor. If it hits the ground, it's a meteorite. A meteoroid storm are fragments traveling in a tight-knit group called micrometeoroids. It's just some terminology. So when the big floating eyeball out in space, the meteoroid swarm is basically coming at you sort of parallel kind of thing. So like all the debris is here and it's coming into the atmosphere. But because of the way we sit on the planet and look up, it appears to be coming out of this radiant thing. So it appears to all be coming here because you're a big floating eyeball in space and all this thing is coming at you, right? And it's sort of like analogous to 1 point perspective or something like that. Like, okay. Here are prominent meteor showers throughout the year. For the summer, we've got June 30th, July 30th, and then August we have some Perseids. Let's see, this one, the Orionids is from Halley, and the Aquarids is also from Halley. Anyway, so it's kind of fun actually in the lab. We might have a lab associated with this. I haven't figured that out yet. Okay, size of meteoroids and damage. So large meteoroids, those of more than a few centimeters in diameter, usually come from the asteroid belt from debris or collisions. So two asteroids smash, makes some stuff, throws it out in the whatever. Meteoroids smaller than a meter across, roughly about a ton in mass, generally burn up in the Earth's atmosphere. Large meteoroids can cause significant damage, though, when they hit Earth. So this is an impact crater. A large meteor, sorry, can create significant damage. This is the Barringer meteor crater in Arizona. Here's the access road, and then I think there's a building right there. And okay, so I've only been here once, and I drove from the highway to the access road, and it was like $17 to go in, and I was supposed to drive another 4 hours to get home to my family, and I was just like, nah. So I didn't spend the $17. Now I kind of wish I had. Anyway, big old place in the big old hole, and they have boulders on the side, because we'll show you in a second how these are formed or whatever, but there's like boulders on the side of the rim here that are about the size of a house. All right, here is another. This is an ancient crater that has eroded, and now we have this circular lake up in Quebec. Here's the Tunguska event from 1908 that I mentioned earlier. There was an airburster, so the meteor came in and exploded over Siberia and knocked down a whole bunch of trees. But they don't think there were any casualties because it was kind of an unpopulated tundra area. So here's the size between the meteoroid, meteorite, etc. Okay, so formation of the solar system. So this is the best guess of how the solar system formed. We're going to talk about this a little bit more when we talk about how a sun forms, or a star, how a star is born. So a nebula is a large cloud of interstellar dust and gas. A solar nebula is a large swirling mass that is destined to become a solar system. And then the nebular theory, which we're going to talk about, solar systems form from a spinning disk that is created when the solar nebula starts spinning rapidly from the nebula collapse. And we've actually seen disks like this in space. So here is the star Beta Pictoris, and it's surrounded by a disk of warm matter, which may indicate planetary formation. So we were able to take sort of this picture. This is visible light. I think this is a drawing, actually, although we do actually have a photograph of an exoplanet, which I thought was really cool. So what happens when we make planets and stuff? So we have a big old nebula here, and it starts to collapse in on itself. So the cloud of gas and dust contracts due to gravity. Somehow something perturbed it, and things started clumping together. With the conservation of angular momentum, which is a physics concept that when you see skaters spin faster when they pull their arms in, so it also will contract. So the inside here, some reason it's spinning faster and it's contracting. More things are coming in. So with the conservation of angular momentum, it says that the product of the radius and the rotation rate must be constant. So therefore, as the dust cloud collapses, the rate of rotation will increase. So just like a figure skater right there. Actually, we met her one time in California. My daughter met her. I think this is Christy Yamaguchi. Anyway. All right, list the major facts and expectations that any theory of solar system formation must explain. So I just took this directly from the book because it was kind of hard to capture it otherwise. Any theory of solar system formation must explain the planet's roughly circular, coplanar, on the same plane, and widely spaced orbits in the same direction around the sun, with the terrestrial planets near the sun and the Jovian planets farther out, as well as the existence of asteroids, Kuiper belts, comets, irregularities such as retrograde motions of planets and moons. Phew, what does that mean? It basically means if we come up with a theory on how planets are formed and planetary systems are formed, it has to actually match what we see. That's basically right there. Because we have a system that has planets in a roughly circular orbit that are coplanar, widely spaced in the same direction around the sun, with the terrestrial planets being close and the Jovian planets farther out. with asteroids, a Kuiper belt, comets, and some irregularities such as retrograde motions, planets, and moons. That's what we have. So any theory that we come up with has to sort of like account for all that stuff. So we're going to talk about the condensation theory of planetary formation. Okay, so, but wait, new data has caused us to rethink this theory. So we had this other theory of the consolidation and everything, but now we have this condensation theory, which I'm going to talk about. The slides don't have much of the old theory, but you'll live. So we now think that the condensation theory is a little bit more accurate description of how solar systems form. So according to the condensation theory, planets form from a solar nebula in 3 stages. So the first stage, dust grains from the solar nebula form this condensation nuclei around which matter begins to accumulate. So 2 things stick together, which attracts a 3rd thing and 4th thing, and it becomes a clump of stuff. So clumps grow as their surface area grow, and they collect more material. This process is called accretion. It's the gradual growth of small objects by collecting and sticking. They create a few objects a few hundred kilometers across, which is pretty big. At the end of this first stage, the solar system has hydrogen and helium gas and millions of little planetesimals, which are about the size of small moons, with strong enough gravitational fields to affect their neighbors. So we started off with just gas and dust, and now we're clumping a lot. Second stage of planetary formation is caused by collisions and merging larger objects and larger objects and larger. And so as the gravitational field grows, they attract more things. So at this point, we have protoplanets, where most of the planetesimal material is being swept up. At the end of the second stage, there are collisions that cause fragmentation, and we have a glowing protosun at the center. That's going to be important when we get to the birth of stars. So in the third stage, which is only really for Jovian planets, the 4 large protoplanets in the outer solar system were so large that they started to sweep up the gas from the solar nebula. So all this gas and dust that was out there, like Jupiter and Saturn, started sucking it all in. But the condensation theory added on to that. So condensation occurs when gas cools and changes its state to become tiny solid particles. So interstellar dust grains act as condensation nuclei. So basically that adds in temperature. So the reason why the inner planets are rocky is because it was too hot for the gas to collect. And so it migrated outward, or it got swept up, and the stuff outward made the gas giants because it was cooler there, and they were able to suck it up like a vacuum. I'll say the condensation theory says the solar nebula contracted on its own gravity and began to spin faster. Protoplanets were okay. I think we've already covered that. Okay, so how does the condensation theory account for the terrestrial and jovial planets? Also from the book, so planets in the outer solar system became so large that they captured hydrogen and helium from the solar nebula, forming the Jovian worlds. When the star became a star, its strong solar winds blew away any remaining nebular gas. The terrestrial planets are rocky because they formed in the hot inner layers of the solar nebula. Farther out, the nebula was cooler, so water and ammonia ice could form. And many leftover planetesimals were ejected into the Oort cloud by the outer planets, leaving the Kuiper belt behind. The planetesimals in the asteroid belt never formed a planet, probably because of Jupiter's gravity. So the material between Mars and Jupiter never was able to form a planet because Jupiter is just so dang big. So here we have a process of possible planetary formation. This is an actual picture. This is in infrared, and this is in radio waves. And so if you can see where these dark lines are, that's where there's some planetesimals potentially sucking up all the material. So also with the condensation theory, temperature in the cloud determines where various materials will condense out. This determines where the rocky planets and gas giants form. So here we are close to the sun here, distance from the sun in astronomical units. So, and they were farther away here. So metals and silicates, rocky material, water, and ammonia. So Earth is ish here, Jupiter is ish there, Saturn is there, and then Uranus is out here. Anyway, so temperature played a role too. Key takeaways: large outer planets must have formed before the sun became strong enough to create a solar wind that removed the excess gas. That's interesting. Temperature in the solar nebula affected what materials were able to condense, so which materials were able to stick together. This is a long, complicated section for this one. The criteria listed for the basis of the theory mostly agrees with the condensation theory. Anomalies are things that are just weird, and we will discuss those coming up. So, okay, planets beyond the solar system. So this is exoplanets. Describe the main methods by which astronomers have detected planets beyond the solar system. This is kind of fun, actually. In the 90s, in the 80s and 90s, before that, of course, but we didn't think that there were any other planets around other stars. We kind of thought there might be, but we hadn't discovered one. So, but we developed some techniques that helped us discover them. So many planets have been discovered in other solar systems. This figure compares recently discovered exoplanets to Neptune and Earth. So basically, here's sort of the names of all of them and ish their size. So we have I told you we have other exotic stars or exotic planets that are not represented in our solar system. But we can compare the planets to if they're a Jupiter, if they're a Neptune, or if they're an Earth kind of thing. The Jupiter ones are easier to discover. And so those were the first ones we were able to discover. We've only discovered a few of them that are close to Earth's size and only a few of them that actually could potentially have liquid water. All right, so some planets are discovered through a wobble that they create in their parent star's orbit. We found about 600 stars this way, and that is because they're big. So if we can kind of catch this wobble on a star, then we could infer that there is a big planet around it. We can calculate how big it is. Okay, oops. Others are discovered through periodic dimming of the star. So this is planetary transits. And so there's a very teeny tiny drop in the brightness of the star when the planet passes in front. So in order to find planets this way, the planet and the star have to be lined up just right. We've discovered about 1,200 exoplanets this way. Pretty cool. So this is sort of a representation. So the orbits have to be lined up just so, and most of the masses are closer to Jupiter than of Earth in order to affect this. So here we don't have the planet in front of the star. Here the star or the planet has moved in front of the star, and then it goes off. And so we'll see the intensity of the light dip a little bit. My master's thesis was on this, and it was very hard. I had a hard time doing that, but that's okay. So here are the orbits of the extrasolar planets that we've discovered so far. So here's like the representative inner sun, and then there's like Earth's orbit, and then this is where all the other planets that we found so far about where they are. So a lot of them are very close to their sun, or their star too. All right, so about 2,000 extrasolar planets have been found so far, orbiting about 1,000 or so stars. We classify them as Jupiters, massive exoplanets, right? We have those. Neptunes, less massive, but still big. Super Earths, which are about 2 to 10 times the mass of the Earth, or about half the mass of a Neptune. We think they're rocky. We have Earths, which are below 2 Earth masses. We have hot planets we classify. So it can be a hot Jupiter, a hot Neptune, a hot Earth. And that's within 1.1 astronomical units to the parent star. So it's very close. If you remember, Mercury is at what, 0.6 or something? Cold planets that are outside of one astronomical unit, so they don't really say cold or whatever. And then hot Jupiters, these are the first exoplanets to be discovered. Their surface temperatures are 1,000 to 2,000 K. And anyway, they were easy to find because they were close, caused a wobble, and they're big. All right. So this plot shows the masses of many of the exoplanets discovered so far. Most have the masses closer to Jupiter or Neptune than Earth. So here is sort of Earth, which is sort of cold and light-ish. So these are Earths. And we've discovered a couple of hot Earths. And then we have super Earths, which are 2 to 10 times. A lot of them are hot. And Neptune is out here. And so these are classified as Neptunes. And of course, Jupiter is here. And these are Jupiters. And these are hot Jupiters. So Jupiter-like planets and hot Jupiters. And as I said before, it's just easier to detect those. So that's why we have so many more of those. We don't know the real like ratio of small planets to large planets. These are just easier for us to detect right now. So the habitable zone is the definition that we have. An area around a star where liquid water can exist on a planet, making it a nice place for life to begin and stay alive. Very nice. So far, we found 13 super Earths and 4 Earths, including our own, that are known to orbit in or near the habitable zone. Oh, so we've got 17 we found so far. But this data is, the book is a little bit old, so this might be updated by now. And here we have a comparison distance from the star and the mass of the star. And then, of course, the habitable zone. So this is where if you take your various stars, they have different temperatures, right? So the red ones are cool and the blue ones are hot. The red ones are small. The blue ones are huge. Here's the sun sort of right in the center. We're going to learn more about that later. And so we have the habitable zone where water can exist, and it's basically just a calculation of how close are you to your sun, how hot is your sun, and how close do you have to be. And so here is Earth, and then here this looks like more than 17, but anyway, there you go. So a lot of Keplers, they're discovered by Kepler. The naming system in astronomy is usually weird, but how we found it, usually the mission in which it was found gets to carry the name. So these were the Kepler missions. Anyway, okay. Okay, and that is it for chapter 4. Let me know if you have any questions. I hope you're enjoying the class so far. Next, we're going to talk about Jovian planets, which is kind of cool. And then we're going to talk about moons, and we're going to talk about some other stuff. So I will see you in the next one. Maybe if I can get the thingy to work. Okay, bye.